127, and here we are. All right, so we're down here. We're just about to spring break. There's no class next week, but today is the second part of Windows overflows and a couple of projects where you perform these overflows in the debugger just so you can see it more explicitly. So let's start with the slides, which are here. All right. All right, and that should be about right. I'm looking at my streaming. Yeah, okay. All right, so we'll talk about stack protection, heap-based buffer overflows, and other overflows. So in GCC, in Linux, if you make a program, here's one we did before that had a buffer overflow. Not that that really matters, but the point is there's a buffer overflow vulnerability in a test PW function, and we're going to see the defenses that the compiler puts on here. So if you compile it with the default, then it will put a stack protector on. If you use this, it will, I think, remove the stack protector. This is with and this is without, I think. And I'm thinking maybe it's backwards. I forget. Let's see if it's from the next slide. So the point is when you disassemble it in, say, the debugger, you will see without a stack protector, this is the test PW function. It will just push the base pointer, which is what always happens on the stack. It pushes the base pointer, it moves the base pointer to the stack pointer, and then subtracts something from the stack pointer. This is what creates a new stack frame, and then it starts doing stuff here. This one here does the same thing, but then it adds these extra functions, where after it's created the stack frame by subtracting 24 from the ESP, it then takes this value from the GS register, 14 beyond it, puts it in EAX, and then moves EAX into a position 12 bytes away from the EBP. So this puts a canary value at the end of the stack frame, 12 bytes from the end. That's what this is. This is a effectively random number. It's copied from somewhere, put at the end of the stack frame, and then when it returns from the function, it will, before it calls the return function, it will move that value from the stack frame into a register and XOR it with this value in the GS14 location. And if it's not equal to 0, then it will call an error, stack check fail, instead of returning. So that is how canary values work. It puts an extra value on the stack frame near the end. So if you have any buffer overflow, it would hit that value before it hit the return pointer. And then it would, before it calls return, it checks to make sure that value has not changed. So this is with the stack protector, and this is without. All right, and you can see the same thing on Windows. All right, so in Windows, you can use Visual Studio, and you can do it. So you can put exactly the same source code in Windows with notepad.cpp and use Microsoft's compiler. And Microsoft's command line compiler is CL. So you can compile it on PWD. You can compile it with just CL or this EHSC, which is some flags I found recommended that I don't think you really need. Just compile it normally, and it will have a stack protector. If you use /GS-, it will remove the stack protector. So when you compare those two, you'll see the PWD, in this case, is 215,552 bytes, and with PWDN, it's 215,040 bytes. So it's about 500 bytes smaller in size because it's missing just a few instructions to implement the stack protector. And we'll do this in the project later. So you can disassemble them with a disassembler like IDA-free, and then you'll see without the stack protector, here it is entering the function, just pushing EBP, subtracting 14 from ESP to make a stack frame, and then it goes right into the functionality asking you to enter a password. But this one creates the stack frame and then takes a security cookie value, moves it into EAX, and puts it on the stack. And when it returns, it's going to do the same thing, checking to see that the security cookie has not changed. So it's exactly the same function. Microsoft calls it a security cookie. Linux calls it a canary. It's the same thing. And therefore, it prevents the kind of buffer overflow we've been doing. All right. So that's called stack protections. In Microsoft, the /GS flag is on by default, so it puts security cookies, and it's a 4-byte value placed after a procedure call. All right, and it's checked before the procedure returns. So here's what the stack looks like with the security cookie. You have your local variables like a string buffer, and then you have the security cookie, and then the saved EBP and the saved return address. So you cannot overflow this and reach either of those without getting caught by changing the cookie. Now, you still can do the kind of buffer overflow we did in the very first buffer overflow project, where you leak from this variable into another variable. This kind of defense cannot prevent that. But it does protect these, the return pointer, which is the main exploitation technique used by most malware up through, say, Windows XP. So now this means it has to generate this cookie value, and that has to be unpredictable. So it has to get a fairly random value. So what it does is it combines a lot of values. The time and interval of nanoseconds, process ID, thread ID, tick count, performance counter, just a bunch of different clocks XORed together to create an effectively random value. And so in principle, if you can run a process on the target system to get the time values, you might be able to predict that cookie by knowing some of those times. And so people have tested it and determined that in principle, here's the percent accuracy prediction, they were able to predict with almost complete certainty many bits in the cookie, but some bits they couldn't. So effectively, even though the cookie is 32 bits long, it only had 17 bits of randomness. So it wasn't as strong as it might be, but you had 2 to the 17. Now 2 to the 10 is 1,000. So this is on the order of 1 million or 250,000 guesses. So that's pretty good, but it's not perfect. So that's 131,000. So an attacker could run the attack 100,000 times. You might be able to just guess the cookie. But you'd have to run 100,000 times to get it by luck. All right, and so you see the security cookie is put in, placed on the stack at a calculated location to protect the EBP and the return value. And the epilogue has this, where you call security check cookie, which is a function that makes sure the cookie has not been modified, and if it has, then it will not continue executing the program and will stop with an error message. All right. Compared to the authoritative section in the data section, if it fails, it calls a security handler to report a failure. All right. Now, another thing that happened, before this, there was another solution where it would just change the order of variables on the stack. Earlier versions of the compiler would just put the variables in the stack in the order in which the programmer put them in the code. But after 2003, or somewhere around here, Microsoft moved all the arrays to the bottom so that you won't have an array leaking into other variables so much. All the arrays will be at the bottom, so if there's only one array, it'll be right at the bottom, and you can't do any overflow without hitting the cookie. And if there's multiple arrays, then the array would leak, if at all, into another array, where it might do less harm. Or one string would just overflow into another string, instead of overflowing into something that would be an integer variable or a pointer, and more likely give you control. So this would lower the exploitability of buffer overflows, where you're unlikely to hit something that directly goes into the EIP. And that's the idea. So in the old days, you'd have name, password, isadmin, for example, here. So by putting in a name that was too long or a password that was too long, you could change this isadmin parameter. But now it would put all the strings at the bottom. So you can't overflow into some other type of data, but just into another string, which is likely to be less harmful. And there you are, before and after overflowing, just showing the book's version of the same thing. You have a buffer. You try to overflow to hit the return address, but you hit the cookie, so you're going to get busted. All right. So, all right, now if you change the cookie, but the parameters are used in a write operation before the function returns, then you might be able to overwrite the authoritative cookie. These are ways to defeat it. If you can control a write operation, you might be able to change the authoritative cookie value in the data section, so your cookie check passes. You might be able to overwrite the handler, so the fail function will be under your control. These are possible ways to defeat this, although I haven't got any hands-on projects where you actually do that. These are a little esoteric. All right, and then we should talk about the heap. In the heap, you can have overflows too. So the purpose of the heap is to have temporary data. So if you have something like a web server, you have these requests coming in, and they might vary in size. And after you process a request, you want to free that memory to handle the next request. So you have to store possibly large bits of data temporarily and then clear them and reuse them. That's what the heap is for. So every process has a process heap. If you turn get process heap, you'll get a handle to that process's heap, and it's also a pointer to it stored in the process environment block. So this is code that returns it. It's FS0x30. That's a pointer that will get you the UVDX, and then take that address plus 18. This will give you the pointer to the process heap. And this is what most of the Windows API functions use. They use the default process heap. You can create dynamic heaps if you want to. Instead of just having the one process heap for your process, you can subdivide it into other heaps used for different purposes with the heap create function. This is what custom software can do, although the Windows API mostly does not do that. So you have the default heap, and then you create more dynamic heaps out of it here. In the process environment block has information about finding those heaps. So you allocate a chunk of memory on the heap with heap allocate. There are other ones called local allocate and global allocate left over. And when you're done with it, you call heap free. So to a pointer, so you allocate some memory, you use it, then you free it so you can reuse that memory for more new data. So the stack grows downwards towards 0, but the heap grows upwards. It starts with 128 entry structures to keep track of the block. Does ASL protection help in heap overflows? It's a good question, and I think it does not, but I do have a project where you can see it. Let's just take a look at that. I think the answer is available. I wrote a project just to test that, and I don't remember the answer, but let me point you to the project. It is, we're going to take a look at 302 and 303, 301 and 302, but I think 303 is the project, which is just extra credit, where you got a program here that prints out some pointers to test these memory locations. So here, viewing memory sections. I wrote, in this case, you're going to make a program called mem.cpp, and it is going to print out a series of addresses here. So you see an address in the text, data, heap, and stack. And when you run this, you can run it a few times and see what changes. And you will see that some areas are subject to ASLR and some are not. So this is the way to do it. So when you do, if you're interested, do Project 303, and you'll be able to directly see which areas are randomized and which ones aren't. And in particular, here, I had, I don't know if I have the answer shown here, but yeah, the stack and heap sections move. So in this case, the heap was protected, but the text and data section never move. So when I compile in the way I did here, which I think was just a default compile, the answer is yes, the stack and heap sections do move, but the text and data sections don't move. But it's a very good question, and I'm sure it depends to some extent on how you compile your code and what version of your compiler you're using. But that's what I found there, and you can do it and get more details. All right, so the main vulnerable heap operation is when you free a node, because here's a general layout of a heap, although this I think is much simpler than the heap that Windows actually uses. This is the original one from Linux, but the general idea is true. You have a pointer to the next node and a pointer to the previous node, and then some data stored, and then another chunk and another chunk. And when you delete this node, you have to update this pointer to point to the next node over here, and you have to update this back pointer to go over there. And think about this operation where you update this back pointer to that address. You're going to be changing a pointer up here to an address which you're fetching from this back pointer. And if I had an overflow here, so I was able to change this value and change that value, then I would be able to change the address you write to and change the data you write to that address. And that is indeed what happens. If you have a heap overflow, you will find a write operation where some of the data you put in is used to determine the address you're writing to, and some of it is determining the data you're writing there. So just like a format string attack, you can now write to an arbitrary location in memory. And we've seen from the format string exploit that if you can write to memory, then you can take over the box, because you can write to something that will eventually end up in the instruction pointer, like overriding a pointer to a library function. Or
if you overflow the cancel block, what can you do with it?
Yeah, if you overflow this block, right? If you overflow this block, you hit the control bytes, and those control a write operation when this block is freed.
But what use can you make of it?
You can take over the machine. Because, see, if you overflow this, you can put in, say, shellcode you got from Metasploit, and then you can hit these control values, which have a write operation, and then you write into a function pointer in the global offset table, something like the exit function is overwritten by an address that points back here. That's how you do it. Yeah, good. Very good question. All right. So there's a lot more to it on heap allocation in Windows involving all these things like the look-aside list and so on, because Microsoft has a lot of complexity to its heap to deal with heap fragmentation and such. So heap overflows can get more complicated. All right, so here's some techniques. You can override a pointer to the exception handler, override a pointer in the process environment block or the unhandled exception filter. These are various ways to get control of the box. And so you can enter a critical section is called whenever a process exits, and the process environment block location is fixed, so you should be able to restore this pointer. I don't quite remember exactly how this works. We don't have a hands-on project for this stuff because it gets sort of intricate. Anyway, Windows 2003 server, it didn't have those pointers, but you could use some loader functions. These are the details which I only describe in general terms because we don't really have a hands-on project to practice them. XP has something called vectored exception handling, and you can use a heap overflow to change information about those handlers. So you override a pointer to the unhandled exception filter, and then you can set this value. And so once you do that, then an exception will go to an address that you can control. Now, if you do an overflow, like you described on the heap, you overflow the next pointer to the next block. Now the heap is broken. And it's pretty easy to detect. Microsoft has a defense rather like Cisco's check heaps, where it just hops to the end of the heaps to make sure it's intact. So you're going to have to fix the heap. So the simplest thing to do is just make the heap look like a fresh, empty heap. You can do that. So you can change the pointers to point like to the start and the end, so it appears to have just one block of data on the heap, and that block is not corrupt. So this is one way to repair the heap so it will pass a test. All right.
When you repair the heap, the function that the program then use the heap to broken there.
That's right. You have collateral damage. Yes, then you've broken some data on the heap. Yes, absolutely. And the same thing's true of our stack overflow exploits. You've noticed they often cause the program to crash. So a very careful exploit will not cause the program to crash, but a sloppy exploit often will. But you're right, if you do this, then you're going to lose the data on the heap. However, the data on the heap is mostly just temporary anyway. So often you can delete it and it won't cause the program to crash. But it will depend on the program. All right, so if you change an exception handler, you're going to have to restore it. Otherwise, real exceptions will not be handled anymore, and your program might get stuck in an endless loop if there's an exception. Right, then there's COM objects. We've talked about these before. COM objects are sort of like DILs. They're objects that are created when needed, so that you can have functions available for the program to call, and they are created on the heap. They load into the heap when needed, as opposed to DILs, which load as separate processes. These COM objects, when you call one, it creates an instance of it, and so the COM classes have interfaces which connect them to a program. So you have a vtable, which is a table of pointers to these COM objects that are in use, rather like the global offset table to the C library functions in Linux. So the COM objects contain data. So you've got, say, an analog tuner device, and it's got various things, double word and a byte and a double word and so on, feeding information in. And so if you can overflow these data fields, then you can overflow into other data, and then you can overflow into the next object's vtable, and then you would be changing the pointers to these objects, and again, it's a form of heap overflow. And another thing about COM objects, a lot of them are really old and really vulnerable, and yet they're still available. Thousands of COM objects, and Microsoft has a special table called the kill bit list, which is known vulnerable COM objects you shouldn't use, and there's hundreds of entries there. So you can circumvent the kill list too, and load these vulnerable COM objects. So it's another type of Windows exploit that's out there. Although, again, I don't have a hands-on project for this. It would be interesting to have one, but I haven't been able to add it to the class yet. And here's a viewer to let you see the COM objects called Ole COM Object Viewer, and you can see there's just tons of them, many categories, each with many objects. These are, I say, analogous to DILs, but they work by being more intimately associated with your program. Windows contains a ton of them. All right. And there's other kinds of overflows. You can have an overflow in the data section. Here, if you define your C source code and you put variables up here that are outside the main or any other function, they go right in the data section. So here's a data section that will have a buffer of 32, and then it will have some other values here. And of course, if you're able to write more than 32 into the buffer, you will overflow in the data section and change those other values. All right, and in principle, you could overflow buffers in the thread environment block, and then change pointers and take control of the machine. There are no public examples of this ever happening, but in principle, that's another type of overflow that might happen. So let's try the Kahoot for 8B. Let me open up another tab here. All right. 8B should be here. There it is. I'll give it a few more seconds. And I'm going to plug in my power. All right, let's give it a shot. All right, so what defense is also called a canary? The security cookie, another word for the same thing, a random value. All right, so what do most API functions use? They use the default process heap. They do not break it up into smaller chunks. All right, so which one has a kill bit list? Those are the COM objects. All right. They're like libraries, a bunch of things provided as part of Windows that can add functionality to your code, but a lot of them are old and vulnerable. All right. And which call is most likely to be exploitable by a heap overflow? And it's heap free. When you free it is when you're very likely to gain control of a writing operation as it tries to repair the pointers to jump over the heap element you just freed. All right. And which one is created when needed by another program? Those are the COM objects. And like I said, we don't have a hands-on project with the COM objects. That would really help to understand this. It'd be nice to sort of use a debugger and see the COM object load and understand how it gets in there. But I don't have that in this version of this course yet. All right. Oopsie daisies. All right, they'll have to tell me who they are if they want their points. But they might not care. And Yohani, I know who that is. The other person is cookies. Okay, I think they also don't care about students, I think. All right. So, that's it for that. Let me stop the recording.